Yes, sir.
So, but then last time, how far we have discussed? Uh, can you remember? Slide is visible.
Yes, sir. The slide is visible, sir.
This slide was shown.
Sir, last time heterojunctions we were talking, sir. After I remember till heterojunction, sir. You were explaining about the heterojunctions, and after that I couldn't hear it.
The structures we have discussed. The structures, surface emitting type LED. No. This structure we have discussed or not? This one? Anybody? Or Harshvardhan?
Sir,
Hello?
can you revise it again, sir?
Yes?
No, sir. No.
Okay, okay. Okay. So heterostructure we have discussed, na? So we have seen this, why heterostructure is here, because you need the sources that must be of high efficiency, high power output, high internal current efficiency, and fast response speed. Right. So high power output, you see that is actually related to power emitted per, I mean, high brightness means uh, power output per unit solar angle per unit area. That will see what are the factors that can be used to increase the power output of LED. Another factor is response speed, that is the delay between the application of pulse and the onset of radiations. That should be also minimum. And high internal efficiency means it's basically it is a combination of electron hole pairs, radiative recombinations. So in that case, the efficiency should be high. That means the fraction of radiative electron hole pairs should be more. I mean, radiative recombinations should be more compared to the other recombinations. Right. So to gauge these three factors, you have to have optical field confinement and charge carrier confinement. And for that regions, you need DH structure, double heterostructures. Any heterostructure, I told you last time, it can be a smaller band gap and larger band gap. Can be PP, can be NP, can be PN, like this thing. These are single heterostructures. NN can be a junction. PP can be a junctions, which is not possible in a homostructure. Right. So one is larger band gap, one is smaller band gap. So this is possible if you consider like the 3-5 compound semiconductors, like say gallium arsenide, gallium aluminum arsenide, like these things. One is smaller band gap, another is larger band gap. The combination can be like these things. So you can have different combinations. One is shown it here, gallium aluminum arsenide. Okay, this is a single heterostructure, but actually for LED you need double heterostructure like NPP, NNP, like these things. Because you need two junctions. Here you can see NPP, three layers are there, but two junctions are there. You see, this is one junction. This is NP, another is PP, another junction is there. So two junctions are there, right? In the analytical diagram, you can see it here. This is the depression regions. In this case, this is the depression regions. So one is N type, another is P type, another is capital P type. Capital means larger band gap. This is EG1, this is EG2, this is EG3. Generally, EG3 and EG1 both are same. Generally, but it can be different also. So when you apply the forward so two junctions, then you see, when you apply the forward bias, it's like these things, you see it here, forward bias, then electrons will be injected from this side and host will be injected from this side. So carrier accumulation will result, and accordingly there will be recombinations. So if these recombinations radiative, then you will get emission of light, right? So you need radiative recombinations in the active regions. So more carriers should be accumulated. So that is possible with the band gap differences, right? So that is a charge carrier confinement. Another is optical field confinement. That is possible if the refractive index of these layers, outside layers, it is smaller than the middle layers, because you see it will behave than optical fiber like these things, core clad. So denser, rarer, denser, rarer, right? So by varying the refractive index differences, you can trap the light energy within these regions. So you need double heterojunctions to satisfy optical field confinement and charge carrier confinement, right? That's why the structure is here. And if you see the LED, it can be two types: surface emitting type LED and edge emitting type LED. Well, this is the different layers is shown it here. You can see it. This is these two layers, the light confinement layers. Two layers, just larger band gap if you seen it here, and the middle layer, this is the active regions. Active regions, right? Active regions where active region where carrier recombination takes place, right? And other layers are substrate and contact, metal contacts. Those things are there, right? So let us see the actual configurations. So if you consider the surface emitting type LED, you can see it here. There are how many layers are there? You see it here. This is these three layers, the DH layers. It can be NPP, capital N, P, small p, capital P. Right. These are these three layers. And the middle layer is the active regions. You see it here, that is mentioned here. And this is substrate. There is a well in the substrate through which a small portion of the fiber is inserted, the fiber pigtail, right? And that is fixed by epoxy resin. And other things are there. You see metal contact, isolations. Here also positive, negative side will be there. So metal contact, heat sink, these things are there. This is the surface emitting type LED. And the properties of this, characteristics of this structure is this: it is 50 active layer, it is 50 micron in diameter and 2.5 micron. বলুন ওখানে আচ্ছা এটা আছে তো এটাকে না খুলে এর উপরে লাগিয়ে দিতে পারেন নিয়ে গিয়ে। এটা খোলা যাবে না তো? না না, এটা ফিক্সড, দাঁড়িয়ে দাঁড়িয়ে থাকবে। ফিক্সড করা আছে, হ্যাঁ ফিক্সড করা আছে ওটা। আচ্ছা আচ্ছা, হ্যাঁ হ্যাঁ। So you see it here, the cluster series, these active regions, it is 50 micron in diameter, 50 microns and 2.5 microns in thickness. And the pattern is Lambertian in the sense that here it is actually a light intensity is same in all directions. But of course it is reduced. It follows the cosine law. Lambertian pattern means it is I0 cosine theta. Right? It is varying in this nature. If it is Lambertian pattern, then it is the relations. Intensity at any other, in the normal it is I0. Any other direction, it follows the cosine I0 cosine theta. And in this structure, upper beam width, it is 120 degree. Upper beam width means where the power is 50%. Here you see it here at certain angles when the power is reduced by 50%. Then that is called the upper beam width. On both sides, theta 60 degree in this side, theta 60 in this side, where power will fall 50% of its peak value. So that is the upper beam width. So that upper beam width, it is 120 degree. And in this case, this in this case, this you see this active layer is perpendicular to the fiber axis, so that the photons are emitted in the forward directions will be coupled into the optical fibers. So this is the surface emitting type LED, right? And another is also most important in fiber optic communication, that is edge emitting type LED. In this case, you see it here. Here waveguide effect is there. I can see it here. Same 3 layers will be there. This is the 3 layers, these 3 layers, but it's track geometry. It is track geometry, and here it is just like waveguide. These 2 layers are the confinement layers. The middle layer is the active layers through which light is emitted in these directions. So and other layers of substrate, metallization, heat sink, the common to same as before, surface emitting types, right? Here you see it here. Here it is fabricated. It is fabricated in such a way that it can behave as an waveguide, and the length of this it is 100 to 150 microns. 100 to 150 microns in the length of the waveguide, and strips width it is around 50 to 70 microns in this case, right? And the pattern you see it is more directional, and you see the emission pattern theta perpendicular, theta parallel, upper beam width it is parallel. When it is parallel to the plane of the active regions, then it is 120 degree. But in the perpendicular directions, it is upper beam width is 25 to 35 degree. So that's why it is highly directional, right? It is just like laser source, this emitter, the edge emitting type LED. So these are the 2 structures that are widely used for fabrication of LED. Now let us see how these other factors will determine how much power is emitted, from this LED, and how their light can be modulated. What are the factors that decide the modulation rate of such LED? Right. So before that, you see to estimate the power emitted by the LED, we have to see the internal current efficiency. How? Let us see what are the factors that decide the internal current efficiency of LED. Now, if you consider simple PN junctions, then you see, and if you this is also PN junctions. What I have discussed, but heterostructure, but it is PN junctions. So in this case, whenever you apply the forward bias, electrons and holes will be injected, and when they recombine, you get emission of light. So if you consider a p-type semiconductors, then electron excess carriers will be electrons because of injections, multi-carrier injections. So electron excess carrier concentrations under forward bias, then it will be under excitations, that is delta n. It will be n minus np0. This n actually it is under excitations, and np0 already will be some carriers will be there because of thermal equilibriums, right? And because of temperatures. So electron concentrations in thermal equilibriums. The difference will give you the excess carrier concentrations. Similarly, for n-type, same thing will be there, delta n to delta p. It will be p minus pn0, where p in n0 is the whole concentrations in thermal equilibriums. And if you consider the charge neutrality in the semiconductors, then delta n must be equal to delta p. And these excess carriers, whether it is excess holes or excess electrons, they will decay exponentially and will reach to the steady state value. So you see it here. In this case, it decays exponentially, delta n equal to delta n0 e to the power minus t by tau. How this equation is built up? Here you see this equation. You can have it if you consider this delta n equal to delta n0 or t equal to initial concentrations, and tau is the here it is tau is the carrier lifetimes and delta n0 is the initial concentrations. Now, if you consider these carrier injections, the carriers are recombined. When the carriers are recombined, then times rate of recombination will be delta n by tau. Tau is the carrier times. Uh, so so whenever there is a recombinations, that means there will be reduction in the carrier density. So minus dn upon dt, that will be minus d delta n upon dt. That is the rate of reduction. And that equal to rate of recombinations. So if you solve these equations with the conditions at initial condition t equal to 0, delta n equal to delta 0, you will get these equations. Delta n equal to that, you have just seen it. Now, so this is excess carrier concentrations. Now, these excess carrier concentrations in the carriers, they can recombine radiatively or they can recombine non-radiatively. Radiative recombinations, it will get the light. Non-radiative recombinations, you can have some other form of energy, say phonon, crystalline vibrations, like these things, you can have it. So, in that case, we are interested in the radiative recombinations. So, eta can be defined in this way. Eta, internal contact efficiency eta, it is fraction of electron hole pairs that recombine radiatively. So, RR, that is means it is the ratio of RR divided by total recombinations, radiative plus non-radiative, and this one radiative recombination rate. So how this rate is determined? Now, if you know, if you tau r is the radiative recombination lifetimes and delta n is excess carrier, then RR will be delta n upon tau r. The same thing for non-radiative recombinations, delta n by tau nr. Tau r is the radiative recombination lifetimes and tau nr is the non-radiative recombination lifetimes. So eta will be the ratio of these two, RR by RR plus NR. Just if you substitute, easily cancel. And if you just write 1 upon tau equal to 1 upon tau r plus 1 tau r, then it will be tau by tau r. That is the most important relations for the important relations for eta and radiative recombination lifetimes. So this, if you see this eta will be high if tau r is reduced, right? Reduced, then eta will be high. But actually, we'll see it. This tau, again in the tau also, tau r, tau nr is here. So effective carrier lifetimes, we'll see it, and it is generally reduced by some different by some factors. So what are the factors that will see it? So lattice mismatch, there can be self-absorptions, diffusion layer, layer of thickness of the active layers. Those things are used. These things actually should be considered. Those things should be considered while calculating the value of eta. Right. In this context, also one thing is this. Diffusion length. That means when the carriers are recombined, they will move a certain distance before the combinations. So that distance is called diffusion length. That distance, it is actually d tau equal to half. How we can have these relations? Suppose current, any current, whenever current flows, it will be due to current electrons and holes. So that is proportional to the gradient of the electron or hole concentrations. So you can write these equations per unit area. And if you consider p-type semiconductors and a thin segment of volume delta A into delta X, delta is the cross-sectional area and delta X is the length of this thin segment. Then the volume will be delta A into delta X, right? Volumes. So in these volumes, if you now consider the carrier combinations, means incoming electrons and outgoing electrons, the difference will give you the rate of accumulations. So you can see it here, rate of accumulations within this elementary volume, that dn upon dt, actually will be proportional to the carriers, incoming carriers at this point x, that is dE, dN, dx x into delta A, and minus the outgoing electrons at this point, that is dE, dN upon dx into delta A into x plus delta x. Right. So if you now expand the second terms, into first term will be same as this one, right? And second term will be d2n upon dx2, right? So first term will be same as this, so first term will cancel. Second term will be these ones, dE d2n upon dx2 delta n into delta x. Where here n actually it is delta n. So replacing n by delta n, we can have as before, rate of recombinations will be delta n upon tau into this volume, and the rate of reduction, rate of accumulation. So this is rate of this is the, so the delta upon tau into delta n delta x is the rate of recombinations, and rate of accumulation is this one just now we have derived. So since it is rate of recombination error is reduced, so here also negative sign will be there. So we can neglect the negative sides, negative signs on both sides. So we will get it d2 delta n upon dx2 times delta e dE, that will be delta n upon tau. So if you just simplify it, it will be this ones. And if you solve it with the boundary conditions, x equal to 0, delta n equal to delta n 0, and at x equal to infinity, delta n equal to 0. So if you substitute, you'll get this delta n 0, that is delta n equal to delta n 0 e to the power minus x by d tau whole to half. This d tau whole to half, it is replaced by LD, that is the diffusion length. LD equal to d tau whole to half. And these things you have seen it in your basic electronics most probably. So on the average, the carriers before recombination can move a certain distance before recombinations, and before recombination means before disappear, they will move a certain distance. That distance is called the diffusion length, and that is that depends upon the diffusion constant and the carrier lifetimes. So in a heterojunctions, right. In the heterojunctions, now we'll analyze this how eta is affected by different parameters, and after that we'll see, once you get the value of eta, we can estimate the power emitted by the LED. So any heterojunction, if you see it, it is characterized by this ratio S by D by LT. And S is the surface recombination velocity, and D by LD, it is the bulk diffusion velocity. Velocity term is used because here unit is centimeter per second. So S. So now S, what is S? Actually, for perfectly reflecting boundary, S will be 0. There will no, all the carriers will be reflected back. And in case of ohmic contact, just opposite, all the carriers will be combined. That times it is called the ohmic contact, and that will be infinity. Ohmic contacts, S will be infinity. But in for practical interface, it will be some value 10 to the power 2 to 10 to the power 4 centimeter per second in these regions, in this range, surface recombinations. So with this now, we can solve the charge quantity equations to get the value of delta n x at certain distance x. That is most important. So previously charge quantity equations, just as before, you can write rate of accumulations equal to rate of recombinations. So the first term represents the rate of recombinations, right? d2 delta n x upon dx2 minus recombinations is delta upon tau into x at certain distance x, that is equal to 0. So these equations, if you solve it, then we can have the value of delta nx within the active regions. And once you get the value of delta nx, then we can calculate the power emitted by the LED, how much power LED can emit. So we have to solve the charge quantity equations. To solve the charge quantity equation, you have to apply the boundary conditions. What are those boundary conditions? If you just think about these three layers, N, P, P, is same as before, it's on it here. NPP, where N gallium aluminum arsenide, P gallium arsenide, and P NPP. So it is P gallium arsenide. So in this, in such three layers, so this is the D. This is the thickness of the active layer T. Now, the first boundary condition is the d delta n upon dx, the variation of excess carriers at x equal to 0. At x equal to 0, you see it here. That will be minus j by qd plus s by d delta n into 0. What is these things? Minus j by d. J by qd is the number of carriers injected. Current, when you apply the current, carriers will be injected. So that is actually minus j by qd. Right. And in this case, it is S by D delta N 0. This is surface recombination. When the carriers are injected, you cannot avoid the surface recombination. Some recombination will be there. So that is actually S by D delta N into 0 initial concentrations at x equal to 0. Not initial concentration at x equal to 0, right? At D equal to at x equal to 0 and x equal to D. So this is delta N0, and here it is at this surface. Oh, okay. This is x equal to 0. X equal to 0, surface recombinations will be there here, and all, as well as carrier injection will be there. So that is the difference. We'll get the d delta n upon dx at x equal to 0. Now at x equal to d here, carriers injected from this side. So here there will be no carrier injections. So the first term will not be present here. Second term will be there, and with the negative signs, because negative signs here it is opposite in natures, surface recombinations and carrier injections. And here it is negative sign easier in because here is concentration gradient. So gradient is negative, that means minus S by D delta N upon delta N into D. Right. So these are the two boundary conditions. Now these two boundary conditions, with the help of these boundary conditions, we can solve the charge continuity equations. What is charge continuity equations? You can see it here. This is the charge continuity equations, D of these ones. So you can see it here. We can assume second order differential equation. So we can assume the solution in these forms: a e to the power x by LD plus b e to the power minus x by LD. Right. Now delta N0 you can find out. Put x equal to 0. A plus b will be there, and delta N d at d it will be x by d. X will be replaced by small d. Right. So we'll get two equations and two variables are there, a and b. So we can estimate the value of a and value of b. So if you just after estimate, you will get very big expressions for delta nx. And once you get the value of delta nx, then you can have average concentrations. That is 1 by d and 0 to d. That is the average concentrations. Right. 1 by d, 0 to d, delta nx into dx. So if you substitute the value of delta nx, it's a very long expression. So you can see it is in Kaiser. So plus you can have it j by qd into tau effective. What is tau effective? Tau effective, the very big expressions again, and it will be f function of tau, parallel times function of this diffusion length, function of surface combinations, and function of d and small d, diffusion constant and thickness of the active layer. This is the tau effectives. It is a function of these parameters. Now this it is a very big expression. This expression can be reduced if you assume the conditions S by d by LD. It is less than 1. Means surface recombination, if you consider, is small compared to the bulk diffusions. D by LD, it is the bulk diffusions. So under these conditions, this equation will be satisfied tau effectives, and it will be just 1 by tau effective equal to 1 by tau plus twice S by D. Right. So you can see it here. So tau effective is now reduced compared to tau. Earlier we have seen this tau equal to eta equal to it is here eta by tau r, that we have seen it, but you see this tau will be reduced because of these things, surface recombinations. So because now actually tau in internal efficiency, tau will be replaced by tau effectives, which is less than tau. If you in this equation, if you compare it, tau effective is less than tau. So eta will be reduced because of surface recognitions. There will be another factor will be there, self-absorptions. Self-absorptions within the active layers, some power will be absorbed, right? Thickness of the active layers. So considering all those things, you can calculate the power emitted by the LED. That is these things already I have mentioned. You see their power emitted by the LED, it will be P equal to Hc by lambda tau r into 0 to d delta nx into e to the power minus alpha x dx. What are those things? Why? How this relation comes? Actually, it is power emitted means P by h nu photon, number of photons equal to number of photons, that will be number of carriers. Hc by lambda means h nu, one photon energy into total number of excess carriers, right? So that you can have it by integrating 0 to d. This is the d is the thickness of the active layer. So we have to integrate how many carriers are present. So delta nx into e to the power minus alpha x lambda into dx. Right. So that is the total power, total carrier recombinations, total carrier, excess carriers divided by tau r, that is the total recombination. Because you have seen is delta n upon tau r, that is the radiative recombinations. So that will give the light. So power emitted will be, this is delta n by tau, delta n into tau r, 1 by tau r. Right. So Hc by lambda tau r times 0 to d into these ones. Right. And this delta nx, we have seen it, how it can be determined. So after substituting this delta nx, you will get Hc by lambda q into eta idh times j. What is eta idh? It is the differential internal quantum efficiency because of self-absorption, and the self-absorption is here, and also because of surface recombinations. So that one is here. So if you just solve it, you'll get these ones, Hc by lambda q into eta idh times j, given the current density. Right. So the power emitted by the LED, it is given by this relations, Planck's constant times velocity of light divided by the wavelength of light. It is the charge, and times internal quantum efficiency times current density J. Right. So this is the power emitted by the LED. This is the most important relations, power emitted by the LED. Now, see, so it depends upon this factor, internal quantum efficiency and current applied, and the, yes. Oh, अच्छा अच्छा, वो अविनाश ना, अविनाश। ये क्या है यार, ये
स्वीट्स है सब, लैब जो भी मतलब है आपकी जीवन लैब।
अच्छा अच्छा, तो इतना स्वीट्स क्या,
नहीं ज्यादा नहीं है, 10 पैकेट है। हम कहें सर दे दें ताकि कोई भी लैब में हो तो
कांग्रेचुलेशन, ना डॉक्टर बन गए। नहीं ठीक है
ठीक है सर।
ओके ओके, थैंक यू। So this is the power emitted by the LED, right? And how now let us see how how the modulation rate is determined by this. modulation rate determine. What factor actually determine the modulation rate of LED? Ultimately, LED will be modulated by the modulating signals. So here you see the factors that will limit the modulation rate. So here actually, if you see the modulation of LED, it is actually limited by the frequency response, right? LED, some capacitive effect will be there. Right? Just a minute. Modulation rate, and you see about the diffusion capacitance. Yes, diffusion capacitance will be there. That will actually limit the modulation rate. What diffusion capacitance? When you apply the current, then some stored charges will be there in the active regions. So there will be some capacitive effect that will limit the frequency response, right? I mean the modulation rate. So when you modulate the light at certain frequency omega, right? Then intensity at that omega that is equal to I0 into 1 plus omega tau effective. Tau actually tau, but now we're replacing tau by tau effective because of surface recombinations, right? So 1 plus omega tau effective square whole to minus half. These relations actually it is taken from this some such papers. This is the widely used expressions for modulation rate of LED. Now, if you in this context, if you want to estimate the modulation bandwidth, then what you have to do, you have to find out the 3 dB bandwidth of the detected electrical power. Means this is the optical intensity. When this light falls on a photodetector, it will create the current. It will produce current, right? That means electrical power will be there. So 3 dB bandwidth of that electrical power will give you the modulation bandwidth. So so when you consider the power at actually in case of this optical when you do the optical intensity power, that power is proportional to the scalar device. LEDs are the scalar device, means it is P omega power detected by the photodetectors. It is actually square of the intensity, right? Square of the intensity. That's why it is P omega proportional to I square omega. And bandwidth corresponds to half power point. So you see for modulation bandwidth, so P omega, that will be P0 by 2. Actually, P delta omega actually it will be. So I square omega, it will be I square 0 by 2. So now we have just now seen this intensity at these ones, I omega, it is I0 times this one. And if we just take the square, then minus half will be minus 1. And if you apply these conditions, half power point, then that times omega will be replaced by delta omega. So after simplifications, you'll get it. Just if you solve it, you'll get it delta omega tau squares. That will be I square 0 by I square omega. That is actually you see it here. That is actually 2 from these equations. You will get it. 1 plus delta tau effective into delta omega square. Half is here because this ratio it is half. You see, I square 0 by I square omega, that is 2, half power point, right? At this point. So it is delta omega into tau effective square will be 2 minus 1, that is 1. And half power bandwidth delta omega, that will be 1 upon tau effectives. That means it is inversely proportional to the effective carrier light times, right? Tau effective. Now, if you consider the power bandwidth product P into delta omega, then P it is, you have seen it is SC by lambda cube eta IDH times J into delta omega, that is 1 upon tau effectives. So, and eta H, it is now, we have seen is tau effective upon tau R. So tau effective will cancel, tau R will be there. So it is HC by lambda to 1 upon tau r times J. So for a fixed injection levels, power bandwidth product remains constant. That means if you consider if you have high bandwidth, then power will be less, right? Or just reverse will be there. Low bandwidth, then high bandwidth means tau effective will be less. It is less means delta omega will be high, tau effective less. Right. And that means faster LED will emit less power. So faster LED will emit less power. That is the meaning of it. So this is the also we can determine this tau r. Okay, it is not there. Yes, tau r. It is relative. How can you determine this tau r relative recombinant lifetimes? That is actually proportional to initial concentration, excess carrier concentration. This is a constant of proportionality, ER. So you can write it. You can. This is the tau r. Right. So we know delta n. It is J by QD into tau r. Right. So with these equations, you can now calculate this tau r. Right. Tau r. It can be these relative recombinant lifetimes can be determined. So anyway, this ultimately what we have seen is this. We have seen this. What is the modulation bandwidth? It depends upon the tau effectives, right? What is tau effective? It is effective carrier lifetimes. That is which is including these surface recombinations. That is tau effectives, right? Effective carrier lifetimes, tau effectives. Only surface recombination is present. And when the LED is modulation, LED modulations, that times intensity will be modulated according to these relations, and the modulation rate will be actually determined by the tau effectives, effective lifetimes. So this completes this LED. What are the things? So LED power, LED modulation rate, modulation bandwidth, the configurations, their heterostructures. You have seen it. तो तुम लोग को कोई क्वेश्चन है तो पूछो. हेलो.
Yes, sir.
एक मिनट. हाँ. ओ अच्छा अच्छा अच्छा. अभी क्लास लेसन जाए नहीं, क्लास के छोड़ दीजिए. अभी हम चर्चा जाएंगे. आएंगे कभी आएंगे. अभी अच्छा छोड़ दीजिए. अच्छा छोड़ दीजिए. थैंक यू थैंक यू. अभी क्लास ले रहे हैं. ठीक ओके. हाँ हर्षवर्धन. बोलो कोई क्वेश्चन है तो पूछो. हेलो.
Yes, sir. Yes, sir.
हाँ बोलो कोई क्वेश्चन है तो पूछो. एलईडी के बारे में कोई क्वेश्चन है तो पूछो जितना पढ़ा है.
Sir, this there in the book, sir?
It is Kaiser. It is there. In Kaiser you can have it.
Yes, sir.
Every expressions, everything's are there in the Kaiser. Power emitted and numerical, from numerical point of view, these relations are important. रिटन एग्जामिनेशन तो ये सब तुम लोग को देखना ही पड़ेगा, इसलिए थोड़ा ध्यान से पढ़ना है एलईडी का. हाँ बताओ.
No, sir. Understood, sir. Just I wanted to ask that.
Okay. Then next time we'll see the laser diode. Today this much for this LED. Right. Laser diode also the same thing will be, their structure will be same, but macroscopically it is same, but microscopically some difference will be there in case of laser diode, because that times feedback will be there. Though it is based on heterostructure, same NPN junctions will be there, laser diode, but feedback will be there. We'll see next times how we can have lasing emission from this heterostructure. Okay, then today this much. Next time we'll see it. If you don't have questions, then just